In this video, we will discuss type 2 improper integrals. In other words, it is an integral which has a discontinuity but does not go to infinity. And as I was mentioning in class last time, the fundamental theorem of calculus can only be applied to an integral which is continuous on the entire interval from a to b, including all endpoints. So if the function is continuous on the entire interval of ab, then the fundamental theorem of calculus holds, which says that, again, if I'm integrating a function of x over a to b inclusive, that would be the antiderivative of the function evaluated at b minus the antiderivative of the function evaluated at a, and all of that will be equal. And again, that will also add up to the area under the curve, if that's true. So what happens if AB is not continuous? If there's either a hole or an asymptote or something like that, then what do we do? And we rephrase these all as a type 2 improper integral. So I think it's helpful this is a suggestion by the book, is that you can think about it in different types of discontinuities about where is such a location, say for example that of a vertical asymptote. But the first case says, well, what if on A to B, it's continuous on everything excluding the endpoint specifically at B? And let's assume that there's a vertical asymptote at B. Let me create a little sketch here to try to illustrate what it's saying. But let's say we're trying to integrate a function from A to B, and at B, there's a vertical asymptote on the curve. And say, the function looks like whatever it does, something like this. And we want to find the area underneath the curve right here. Essentially, if there's a vertical asymptote, notice it's very similar to a type 1 improper integral because it has a portion of area which literally goes upwards forever, right? Whether it's a vertical or horizontal asymptote, it's a pattern that gets closer and closer and closer to that asymptote without touching, which implies that really this is going up infinitely, and this will be an infinite portion of area. Well, again, the question is the area under the curve convergent, aka infinite or other, or does it I said that wrong. Is it divergent, aka either infinite or other, or does it converge? Is it finite? Is it bounded above by a particular value? And notice what the strategy is very similar. So if that potential discontinuity occurs at B, then what we want to do is extract it in the form of a limit instead of just evaluating to B, because again, we're not allowed to evaluate at B since it is not continuous by fundamental theorem. But if we say figure out what's the limit as it approaches B, it will be continuous from A to T, where T is a little bit to the left of B. We can figure out the pattern of what happens as we get close and then evaluate the limit of such a value. And this will amount to help us to solve the area underneath the curve, again, assuming it does converge. Now, similarly, let's say our vertical asymptote was at A instead of B. So let's say that that's A and B is over here, and we had a vertical asymptote going down like that instead. And again, we wanted to consider the area underneath such a function with a discontinuity at the left side instead of the right side. Well, now here we would need to extract A as the limit and check out what's happening as we get closer and closer from the right. Because again, since it's not defined at A, you cannot use the fundamental theorem of calculus to solve such a problem. If you do, you're going to get a weird answer or something that's just plain wrong. Basically I could check out what happens from T to B, where T would be a little to the right of A, and then we could check the limit as T approaches A from the right. And this plus should be look like an exponent. It looks like it's just a graphical typo in the notation. Or similarly, if there was a discontinuity in the middle, we would want to split it up into two pieces, kind of like we did in the last example. But we'll come back to that in just a minute. Let's get into an example. Don't want to talk on and on and on without doing any math. So noticing our first example, notice how this integral looks very similar to what we were just working on. And again, notice it's very typical to be looking at rational functions or exponentials or stuff, basically things which have vertical asymptotes as well as horizontal asymptotes. Those are where improper integrals are more relevant. But notice at 0, this function is discontinuous. So let's say I didn't realize that this function was this was an improper integral. and I just tried to solve it willy-nilly. Well, we could, the antiderivative of 1 over x squared is negative 1 over x, and I could try to evaluate this from 0 to 2. But notice very quickly we're going to run into an issue because 1 over 0 is not defined. So you could come to the conclusion, well, this is undefined, this is divergent. But that actually may be correct, but technically you can get the wrong answer by trying to think that way. And again, doing that is not allowed. That function is not continuous at 0. So that is, again, math garbage. That is not proper because, again, not allowed to do that when it is not continuous. So if it's not continuous, or again, you can kind of recognize this by realizing that 0 is not within the domain of this function, which means there's a problem. And so again, how do we deal with such a problem? We need to extract that discontinuity as a limit. So what I'd write it as the limit as t approaches 0. And also another thing that you need to kind of practice is figuring out, okay, is this from the left or from the right? But a way you could remember it is if it's on the bottom, the limit will always be coming from the right. And if it's on, if you're extracting the number from the top, it will always be coming from the left. But again, logically speaking, if you just imagine what this problem represents, right, we could think about 1 over x squared, which has a graph that looks something like that. If we're integrating from 0 to 2, that means it's all the way, since it has a vertical asymptote, it would be going from all the way from 0 all the way to there. Oops, sorry, you guys can't see what I am drawing. My apologies. But 1 over x squared is sort of like a reciprocal function, but I have the drawing on your packet. I'm silly. But, again, it would be like the area from here to here from 0 to 2. And since this goes up towards infinity, the question is, well, does this amount to be a finite area or not? But notice how the limit as t approaches 0, it's coming from the right? Because it's not from the left. That is not a relevant portion of area. So summary, we need to do the right-handed limit here. And it is important that you pick the correct direction. If you pick the wrong direction, or if you do not do a directional limit, you might just be plain wrong because the directionality of the limit has to make sense. So just like, from here, everything is exactly the same as a type 1 improper integral. We need to solve the integral, plug in the boundaries, and then figure out the limit ultimately. Now, another obvious difference is we're not taking the limit towards infinity. We're taking the limit towards a specific number directionally. So again, I'm going to leave my limit alone until I figure out my integral. But we already know the antiderivative of 1 over x squared is negative 1 over x from t to 2. Because we did this one, in class, but obviously by power rule. And plugging in the boundaries before I start thinking about solving the limit. I will get negative 1/2 plus 1 over t. Because again, it would be minus a negative. It'd be minus a negative 1 over t, which would turn into plus. And notice this is a key difference. So again, the limit of a constant is always a constant, so this will do nothing to the negative 1/2. But the limit of 1 over t is not 0. When we took the limit to infinity, this part did head to 0, but the limit of 1 over t as it heads to 0 from the right would actually go to infinity. So this guy goes to infinity, and what that means is our integral diverges. So also another thing about how to write your answer, you might want to say, well, is the answer infinity? Is this an infinite amount of area? But when it comes to series and infinite area chunks or whatever, however you want to say it, the term diverges is more proper because if it is not finite, the implication is it's either infinite or sometimes infinity we might not be able to figure out if it is a finite value, or certain combinations of infinity can be too confusing. So basically, infinity is not the correct answer here. Diverges is the correct answer, and it's just a sort of a way of saying this is not finite. And it could be minus infinity, or it could be infinity. It could just not exist at all. There's a lot of different things that diverges, that statement includes, but saying infinity is not generally accepted, even though, as we can see, this is an infinite, this amount of area does appear to be infinite. So this is a good place to pause. In the next video, we will do a couple more type 2 improper integrals.